Namaste. Today we will discuss about the thin shock layer theory, right? And you know very well that from the basic we have already studied that thin shock layer is the layer between the shock and the body, right? So in many cases we have studied something called beta minus theta, where beta is the shock angle and theta is the body wedge angle, right? So let us have a discussion on the thin shock layer theory. Now, okay, I acknowledge hypersonic and high temperature gas dynamics by John D. Anderson. So let us start our discussion on thin shock layer theory, right? So basically, the assumption which we have made is that the thin shock layer, right? That means that the shock is very much closer to the body, right? Which in turn leads to a small volume between the shock and the body. So here we can say that we assume thin shock layer, right? So that means that the space between the shock and the body is of small volume, right? The space between shock and the body is of small volume, right? So if that is the point, then for a very high Mach number, the flow over a generic hypersonic configuration, say let us consider the flow over generic hypersonic configuration. So for a generic hypersonic configuration at very high Mach number, right? We can say that at very high Mach number, right? Very high Mach number. So in such a situation, right? And here let us consider gamma is equal to 1, then we know the relation beta by theta that can be equated to gamma plus 1 by 2. That becomes like beta almost equal to theta, right? So the observation here is the shock angle and the Mach angle are almost equal in the hypersonic flow regime, right? So this is applicable only by considering the Mach number m infinity is hypersonic and very high, and also the assumption of gamma is equal to 1, right? So if you consider that for such high Mach number, right? So within the shock layer, we will have the same equation for the shock, body, and any other streamline in the shock, right? So it is valid because you consider, in our case, we consider beta is almost equal to theta. Then the same equation can be applicable for shock, body, and any streamline in the shock, right? So let us say, that the same equation, equation can be applicable applicable, right? So the same equation can be applicable for body, shock, and any streamline, right? Any streamline in between. So this is the basic assumption of the thin shock layer. So this is the basic assumption of thin shock layer theory, right? So the basic assumption. Now let us consider a body, right? So let us say here. So let us consider a body. Here you have a body, right? Let us consider a body and shock, right? For this particular body, you have a shock here. Here, the coordinate system is in such that, right, x-axis is parallel to the shock, right? Say we consider this x-axis parallel to the shock and the y-axis which is perpendicular to the shock. X-axis is parallel to the shock and y-axis is perpendicular to the shock. Also, let us consider the velocity component u. So the velocity component u and the velocity component v are the velocities in x and y directions respectively, right? So x and y directions respectively. So let us assume the flow to be two-dimensional, right? In this case, we can have the flow is two-dimensional, right? One is two-dimensional and another one is x, y, the corresponding velocity is uv, and before that the x is parallel to the shock and y is perpendicular to the shock, right? Now, okay, now let us write the momentum equation, right? Let us write the momentum equation, right? We can write the momentum equation. Let us write the momentum equation for the given coordinate system. For the given coordinate system. So we can write that as rho u square by r, that is equal to the pressure, change in pressure, dou p by dou n. So here, since our assumption include thin shock layer and the equation is same for shock, streamline and the body, let us have a consideration r, right? So you know that the r is the local radius of curvature. Here we have a r, that is the local radius of curvature, r is the local radius of curvature. So please remember other things like the rho is density and the u is the velocity component in x direction and p is the pressure and so on, right? Now I can write the same equation, say rho u square by rs, right? Rs is the shock radius of curvature, I can write. So this can be written as dou p by dou y. N is a normal vector, hence we can say that the y, in this case, we can write y. So Rs is the shock radius of curvature. Shock radius of curvature. right? Now, let us consider the streamline, right? Now we have considered the shock, body, and now the streamline. So we can say that the streamline, okay, for the sake of understanding, I would like to show you the streamline, right? Here you have a streamline, the assumed shock here, and the body calculated, or you know that this is the body and you have a streamline, right? So now we need not to go deeper into that, right? We will discuss. So actually, the idea here is the body shape we need to determine from the shock. This is a kind of inverted method, right? So we say that this is an inverted method where we calculate the body shape based on shock, not the shock based on body shape, right? That is straight method. So let us assume, let us say we have a streamline, right? Here we have a streamline. So let us have a streamline notation of psi. So let us define the stream function, right? Let us define the stream function. So we can write rho u is equal to d psi by dy, right? We have already studied this in fourth semester aerodynamics probably, right? So we can write a dy is equal to, so dy can be equated to d psi by rho u, right? So in the equation we already have here is dou rho u square by r, that is equal to dp by dn, or dou p by dou y in the shock. So we can consider that we can substitute this dy there, right? So we can substitute this in the equation, shock equation. So what is that shock equation? Rho u square is equal to, right, rho u square by rs, right? Rho u square by rs is equal to so rho u square by rs is equal to dou p by dou y. So now let us substitute this dy in this equation, and then write it here. So rho u square by rs, that is equal to dp by dy. I write dy is equal to d psi, and this can be written as rho u. So we can cancel the rho, then u square, right? So finally we can write the equation dou p by dou y is equal to dou p by dou psi is equal to u by r, right? So let us write the equation. Dou p by dou psi, that can be equated to u by rs, and rs is the shock radius of curvature, and u is the local velocity component in x direction. So as we know, we have a earlier diamond, earlier assumption which we made as a thin shock layer. We can consider that U is equal to US. So US is the velocity just behind the shock, right? Here we can say that US is the velocity just behind the shock, right? And we can further discuss that, right? And dou p by dou what psi, dou p by dou psi can be written as u s by r s, right? So we can say that the streamlines are parallel to the shock, right? And finally, we can write the equation dou p by dou psi is equal to us by rs. Now, we can integrate this equation between the point in the shock layer where the value of stream function as psi and just behind the shock layer, right? So just behind the shock layer, we can say that just behind the shock layer, right? Just behind the shock layer, we can write psi is equal to psi s, right? So we can write here the equation. Right? We have equation here dou p by dou psi equal to us by r. So we have dou p by dou dou p by dou psi. So dou p by dou psi is equal to us by rs, and now we can integrate the equation between the point in the shock layer, right, where the stream function as psi and just behind the shock layer it is psi s, right? So we can write that the pressure P of x comma psi, we can write that P s of x plus u s of x by r s of x, and here we can write it is psi minus psi s, right? So actually we want to arrive this particular point, right? This is the crux of this particular theory. And see, from this equation, we can build an inverse method, right? So we can build an inverse method where a shock wave shape will be assumed for the body to solve the above equation, and then we can obtain the shape and the pressure distribution over the body, right? Right. So shock wave shape can be assumed initially, and then we can solve the equation which is shown here, and we can obtain the shape of the body as well as the pressure distribution around the body, right? So we can also go in the other way, right? The equation, the obtained body shape, when it matches with the real shape of the body, then we can get to the shock shape and the pressure distribution also. Okay. So this is actually the crux of the Maslen's method, right? So we will have a detailed discussion of the Maslen's method the procedure, the detailed procedure of the Maslen's method by considering the streamline and all, right? With considering the streamline from point 1 to 3 and the psi 1 and all these things we will discuss in the next class, right? So this is very simple. Initially, we will have a summary of the thin shock layer theory. Initially, the assumption is the shock layer is so thin where the space between the shock and the body is of very small volume, and the flow over a generic hypersonic configuration at a very high Mach number m infinity, and the gamma, the specific ratio is equal to 1, then the beta by theta is equal to gamma plus 1 by 2, which will become the beta is almost equal to theta, right? So now we have a condition that the equation which we apply for the body, shock and the streamline are all same, right? Because beta is equal to theta, so and equal to psi if you consider the stream function, then everything is equal. So this is the basic assumption we have in the thin shock layer theory. So let us draw here the body, then we have a shock for the particular body and having a streamline, right? And for a streamline, the stream function is psi, right? So in the shock, we consider in the shock direction it is x, and perpendicular to that it is y, and the corresponding u and v are the x and y component velocities, and we are considering this as 2d, and r is the radius of curvature, local radius of curvature. For shock it is rs, we assume, right? So we write the momentum equation for the given coordinate system, that is rho u square by r is equal to dou p by dou n, and r is the local radius of curvature. And since we have assumption that the body, shock and all are equal, then we consider rho u square by rs is equal to dou p by dou y, and rs is the shock radius of curvature, right? So when we define the stream function, we know that rho u can be defined as d psi by dy. So dy can be written as d psi by rho u. And here, when you substitute the dy in this equation, we can finally get the dou p by dou psi is equal to u by rs. And we know that the shock, the velocity on the shock and in the body are equal, hence the consideration u is equal to us, and we write this equation. And when we integrate the equation between the point in shock layer where the value of the stream function is psi, and just behind the shock it is psi s, right? So in that case we can write this equation finally as p of x comma psi is equal to p of x, ps of x plus us of x by rs of x into psi minus psi s, right? Here we can write this is psi s of x. This psi s of x, right? So this is the crux of the Maslen's method, and we will have a detailed discussion, right, of the Maslen's procedure in the next class, right? I stop at this point, right? So Maslen's procedure we will apply in the next class, and we will discuss some of the results of the Maslen's method of obtaining the effective body shape from the shock, right? So thank you very much. I stop at this point.